Hi everyone. I'm pleased to announce our next speaker and our first workshop of the day. Today we have Nicole White, who will be doing a workshop on Neo4j. I think this event is going swimmingly so far, but I think you're really going to enjoy this session. And so I'd like if you could join me in a round of applause for Nicole White.
Right, thank you. Okay, so I'm Nicole White. I'm a data scientist at Neo4j. And today, this course is titled Fundamentals of Neo4j. Who here knows what Neo4j is? Okay, so while I'll do a little intro to Neo4j, I'll keep it really short because we don't have a lot of time. But while I'm doing that, please try to navigate to these two links. They're gonna make or break your experience today. bit.ly/dfw-data is the data set that you want to copy and paste into Neo4j. Hopefully you already have it running. If not, please spend the next 5 minutes getting that done. Neo4j.com, you should be able to download from there. And then all the slides that I'll be going through today, or at least as much as we get through today, is at dfw-slides. So dfw-data and dfw-slides. So the slides up here are just point you to an HTML file that you can scroll through on your own, because I'm sure it's hard to see in the back. And then the data set is just raw text file. You're going to copy and paste that into Neo4j. I'll show you how to do that in a second. But while I ramble on about what Neo4j is, please get this figured out so we can get started right after that. So, for those of you who do not know what Neo4j is, I have a very short "What is Neo4j" slideshow for you. All right, fundamentals of Neo4j. Let's get started. So first, what is a graph? This is our agenda for the next 5 minutes. What is Neo4j? And then a quick data modeling exercise. And by that I mean we're going to take what you already know, which is probably SQL or relational databases, and then translate that into Neo4j. And then we're not going to do the browser demo. That's going to be the rest of the training, or the workshop, rather. Probably of today. Okay, are these graphs? Excellent. Someone said, no, they're charts. That's exactly right. Those are not graphs, those are charts. There's a bar chart, there's a line chart. At Neo4j, when we talk about a graph, this is what we're talking about. It's a collection of nodes that are connected by relationships. So that's what we mean when we say graph at Neo4j. So what is Neo4j then? So Neo4j is a graph database. And graph database is in the NoSQL category. And depending on who you ask, that means not SQL or not only SQL. Long story short, it's not a relational database. It's not a layer on top of a relational database. It's a native graph database, as we like to call it. And it was founded in Sweden. So here we have a graph of nodes and relationships, similar to what we saw earlier. But we might want to say more about this graph. We might want to say that the language in Sweden is Swedish. We might want to say that Neo4j, open source property, is true. And we might want to say that it was founded in the year 2007 in Sweden. And this is what we call the property graph at Neo4j. And that's how you store your data in Neo4j. You store your data as a property graph, and you query it as a property graph. And I think that will make more sense as we start getting into an actual query. So this is Neo4j in a nutshell. Okay, let's do a quick data modeling exercise from SQL to Neo4j. Who here has written a SQL query in their life? Oh, I'm so sorry. No, I'm just kidding. I'm happy that I don't write SQL anymore. But yeah, I used to work very heavily in SQL, and now I only work in Neo4j. But we're going to take a quick journey from SQL to Neo4j. So let's say you have something like YouTube data, where you have let's simplify it down to the users and channels. So, of course, you'll have a users table with a primary key of some sort, and then a username field, maybe a password field. field, what have you. And then you'll have a separate table for all the channels that users can create, again, with some primary key, and then the name of the channel, probably some other fields thrown in there. And then if you want to capture users creating channels, the data about users creating channels, you probably have a separate table for that, because multiple users can create multiple channels, right? I can have 3 channels, some users might have 0. So that's usually modeled as its own table, where it has just 2 fields typically, each pointing back with foreign keys to their respective parent tables, I guess. So here we have something called users channel saying this user 2, created channel 1. And then to write a query that gets all of this information, you have to join across all 3 of these tables, right? And then similarly, let's say you also wanted to capture users subscribing to other channels. So I can create channels, but I can also subscribe to other people's channels. That's again another table that you would create. Again, same idea here, where you have two fields typically, each with foreign keys back to their respective tables. This is a very classic, straightforward way that you model something in the relational world. And then of course, if you wanted to query information involving all of this data, you'd have to do joins across all of these tables, if of course you want to get the names of the channels and users. And then unrelatedly, relatedly rather, when you want to ask questions about how one user is connected to another user, it's hard to, when you look at the way you model your data in relational, it's hard to answer that question just looking at the data here. And it's also hard to answer that question when you write a SQL query, especially if it's an arbitrary question like, how is Charles related to David? Does Charles, does he subscribe to a channel that was created by David, or is it more complicated than that? Does Charles subscribe to a channel that was created by someone else who subscribes to a channel? So it could be 1 hop, it could be 4, you don't know. So it's hard to write these kinds of arbitrary questions in SQL. So let's look at how we would model this in Neo4j. So, like I said earlier, in Neo4j, you have nodes and relationships. And then you also have node types that we call labels. So you have a user label in Neo4j, and those are going to be blue. And then you have a different label for your channel nodes, and those are going to be green. So these are different labeled nodes in Neo4j. And then we would put properties on these nodes. So instead of a field in a table, you have properties, key value pairs on these entities. And properties can be both on nodes and relationships. So you have a name property on all of these user nodes, saying name Bob and name Alice. And then you have a name on all of the channel nodes, saying this is the name of the channel. So again, no fields in tables, it's properties on nodes. And then to capture the information, this user created this channel, you would create a relationship. And relationships are also typed. So we have relationship types and we have node labels. So here we have that we have an operates types relationship that's directed from a user to a channel, saying this user, you could have called it whatever you want. You could say user created channel. For some reason I decided to say user operates channel. So here we see Charles operates this channel, cooking with Charles, right? And you can see that this node Alice doesn't have any outgoing operates relationships because she hasn't created any channels. And there's no sense of null values in Neo4j. If the data is not there, it doesn't exist. The relationship doesn't exist if the data is not there. There's no null fields like there is in SQL or in relation. And then to also capture which users are subscribing to which channels, that's a different type of relationship that we would create in the graph. So here we have users subscribed to channels. And then now with our data modeled like this, it's very easy to ask and answer questions with the query language that we're about to go through for the next hour or so. To answer questions like, how is Charles related to David? So here we see Charles is related to David in a couple of ways. Charles subscribes to a channel that Bob operates, and Bob subscribes to a channel that David operates. And it's very easy to ask that question in a graph, whereas SQL, you have join tables on themselves over and over and use some complicated connect by and stuff like that. If you've gone down that rabbit hole, you probably know what I'm talking about. But this is how you model your data in Neo4j as a property graph with different types of nodes that we call node labels and different types of relationships that we call relationship types. So So that is my intro to Neo4j. And now we're going to go back to here. Who got the data imported? Okay. Get out of here.
Can you just tell us how to do it?
Yeah, sorry. That's probably an unfair assumption by me. Okay, so who has Neo4j started? Okay, excellent. So let's pretend that doesn't exist. Don't do this. Okay, so you've gotten to this point, hopefully. You probably have your welcome screen in here. So what you're going to do is you're going to go to bit.ly/dfw-data, and it will get you to something like this. Has everyone gotten to the raw text file of stuff? Don't worry about what's going on here. We're just going to copy paste it. So we're going to copy paste this raw text. That's it, bit.ly/dfw-data. And we're going to go over into our Neo4j's and paste that into the bar up top, right? And then we're going to click the arrow button, and that will create the data set that we're going to be working with today. Everyone follow?
One more time.
Yeah, so we're going to go to bit.ly/dfw-data. It's in the slides right here. Go to this top link, bit.ly/dfw-data. You're going to get to a raw text file. You're just going to copy paste the entire contents into the query bar at the top of running Neo4j instance. And then click the green arrow run button. And then you should get a picture something like this. So now who has the data set? Okay, good enough for me. Let's go through this example data set that we're going to be working with. So for the bulk of today, or all of today rather, is going to be on writing Cypher. Cypher is Neo4j's graph query language, and it's going to allow us to read data from our graph. So this is our data set for today. It's Dallas-Fort Worth places. Who's flown from Dallas-Fort Worth? Okay, good. I think it's a pretty fun airport. But so we have some stuff modeled in Neo4j from Dallas-Fort Worth. We have all of the bars and shops and restaurants and whatnot within all the different terminals. So here we have a few different node labels, which you can see at this legend that it gives you up here. Your colors might be different from mine, and you can change them by clicking on one of the colors in the legend, and then you can go down in the bottom and pick different colors and sizes, and you can pick which property you want to display. So you can mess with that on your own time, I suppose. But we have different node labels here. We have categories, gates, places, terminals, and users. So we have a place, Auntie Anne's Pretzels, my favorite place in Dallas-Fort Worth, is in the category desserts and snacks. So here we have a place node with label place, it's yellow, that has an outgoing in-category relationship to a category node, which the category nodes are in green. And then we also have captured the gate location of these places. So we have Auntie Anne's Pretzels is at gate 39 in terminal A. So it points to the gate, and then the gate points to the terminal. So we have at gate, and then we have in terminal, terminal A. And we see that it's also at gate 22 in terminal C. So all the locations, it's going to have an at gate relationship to the gate, and then the gate will point to which terminal that gate is in, because there's going to be a gate 1 in both terminal A, B, C, D. So there's going to be separate gate nodes for that. And finally, we have some users that are simulated on top of this data. It's kind of Facebook-esque data where they can be friends with each other and like things. And that'll allow us to do some more graphy queries later. So we simulated some user data. So we have a handful of users in this graph, and they can be friends with each other with a friends with relationship. And they can also like things. So we see that Hank is friends with Eli, And Hank has liked Auntie Anne's pretzels. And also notice, when you click on the like relationship, there's a score property on it. So hypothetically, these users give these places scores. And that's captured as a property on the relationship, because remember, you can put properties on relationships in Neo4j. And then finally, users can check into places, saying, I was here. And that's just a relationship. There's nothing more to it than that. So that is the gist of our data set today. We'll get more familiar with it as we start writing queries. But let's jump into the slides. And again, these slides, all the slides that I'm going to be going through are at dfw-slides, that link. So if you're in the back and it's hard to see, you can follow along with me in Chrome or whatever your browser is. Okay. Right, so our agenda today for the next hour, we'll get through as much as we can, is to talk about the syntax basics of Cypher. We'll do a lot of read queries at first, match and return, and then we'll look at constraints and indexes, the schema that you have available to you in Neo4j. And time permitting, we'll look at load CSV, which is an import tool for Neo4j to import your own data. All right, let's look at the syntax basics. So in Cypher, we like to say that you are essentially drawing ASCII art to query your graph. So to draw nodes, you draw parentheses. To draw relationships, you draw open and close square brackets. And then to draw paths, you put hyphens between these things. So you have node, hyphen, relationship, hyphen, node, typically. And then optionally, you can specify a direction with the greater than and less than signs. So here, the first path is an arbitrary direction, meaning we don't care which way the relationship is pointing. We want to query it regardless. We have a left to right in the second row here, and then we have a right to left. So that's how you draw paths in Neo4j, is with nodes and relationships, where nodes are open and closed parentheses, and relationships are open and closed square brackets. And eventually we'll fill these in with more information, saying, I only want this type of node or this type of relationship. So let's look at our very first example of a Cypher query. So the first thing to learn is the match clause, and this is where you actually draw the graph pattern that you're interested in. And so I said earlier that you draw nodes with parentheses. And here, we're matching on all the nodes with label terminal. Remember we had 5 terminal labels in there, terminal nodes, A, B, C, D, E, I think. And in this query, T is what we call an identifier. It's just a variable. You're essentially binding that node to this variable within the scope of this query and using that variable in the return clause to say, I want to return this. So instead of select, whatever from table, it's kind of switched. It's match this and now return these things. So in this query, we're only matching on nodes. We haven't specified any paths yet. We're matching on terminals where T is an identifier and terminal is a node label. And you specify labels with the colon. So anytime you use a colon in a match clause, this is true for both node labels and relationship types, is you're saying, I want this type of thing. I want this type of node, or I want this type of relationship. So that's what colons end up doing in the match clause. So here we're matching on terminals and returning all of them. So this should give you a visual result in the Neo4j browser. It should just show you the 5 terminal nodes. And I just want to drive home that these identifiers, the T that I mentioned in the last query, are totally arbitrary. They can do whatever you want. It's just a variable. So here I have x colon terminal. I found it to a variable x, and I'm returning x. It's just personal preference. You can call it something more descriptive. You can do something really vague like ABC. It's just a variable name. Whatever precedes your colon is just a variable.
You have to do both of those commands on one line.
Yes, this is one query. So you would actually let's do some browser tips and tricks session. So if you control enter, it's going to run your query. So you don't have to keep clicking. So control enter will run your query. This is what you should have gotten. All all your nodes, your terminal nodes should have been returned here. If you hit escape, it's going to expand this window down. Your query window will expand every, if you hit escape, it will toggle this. Shift enter will insert new lines without running the query. I'll probably think of some more as we continue. But control enter will run your query. Shift enter to insert new lines. And to go through your history, it's command up arrow, just like it would be anywhere else. Your up arrow is going to go through all your history. Colon clear in the browser will clear all your past output. The browser will start getting sluggish if you leave a bunch of visual results sitting in there. So colon clear will get rid of all of that and we'll start from scratch. But your history is still there. So if you command up, your history is still there. All right, let's actually draw a path. More than likely, you'll be drawing paths in match clause instead of just individual nodes. So this is similar to what I showed earlier, where I said that to draw a path, you draw a node and then a hyphen and then a relationship, and then optionally a direction to another node. So here we're matching on the in-terminal relationships outgoing from a gate node to a terminal node. And we put identifiers on every entity in the path. We've G, R, and T are identifiers. Gate and terminal on the left and on the right are node labels. And then in-terminal is a relationship type. So again, all the colons are saying, I want something of this type. And that's all being thrown into the match clause. And then we're referring to those variables in the return clause and returning them. So this should give you a bit more information in your visual result in the Neo4j browser, which should show you all the gates and all the in-terminal relationships that those gates have to their respective terminals.
So in table view, if they have more than one properties, what would it display?
In table view.
I mean, when you run the query, you got GRT, right?
Yeah, actually, I think I'm going to answer your question in a slide coming up on tabular versus graph results. So any type. Right, so this should give you visual results somewhere. Sometimes it's hidden, you can drag it. So there's all the gates in terminal D. There's probably another one somewhere. I can't zoom out. That's the thing about visual results, you can lose them. They're there, trust me. I just can't find them. Yeah, the browser will give you this nice, fun visual results. So these are all the gates, and our query matched on all the internal relationships, on both the gates, the internal relationship, and the terminal. We returned all of that stuff, so it's showing us all that information. And finally, so I'm covering right now all the different ways you can use identifiers in a match clause. So we've assigned both nodes and relationships to identifiers. In the previous query, we assigned the nodes and relationships individually to identifiers, but you can also assign entire paths to a single identifier. So in this query, it's the same exact query. There's no performance difference. There's no difference at all, really. It's just we've assigned the entire path to an identifier P and return P. So it's just a shortened way to do what we just did. So you can assign nodes, relationships, and entire paths to identifiers. If you want to assign a path, you do identifier equals path in the match clause, and then you can return it. And yeah, I think the notes say what I just said.
Is there like a zoom out or something? I'll see the graph better.
I mean, you can zoom out in Chrome. That's about as much as it offers. There's been a lot of drama within Neo4j on whether or not to offer zoom in and zoom out. I don't know why it happens, but you have to pretty much zoom out within Chrome. doesn't work so great, yeah.
I mean, it literally doesn't work. It doesn't zoom out that.
Well, yeah, it'll zoom out in Chrome, but it won't zoom out like
Yeah,
for
exactly.
graph. So, well, I mean, I guess if you go
Can you
into
make the font smaller by hitting Command minus?
For real.
yeah, so if you okay, so if you click this thing right here, full screen, click the full screen button, and then zoom out, and then you'll get all here. But yeah, it's not ideal.
It's not exactly. It's literally making the browser font smaller.
Yeah, it's not perfect. That's what you have to do if you want to do that. Anyway, okay, so I think this answers your question from earlier. So graph versus tabular results. All of our previous queries were graph results. We got a visual result in the browser. So when we asked for these terminals, we got the actual nodes, and that's because in the return clause, we're returning the actual entity. We're returning the entire node itself, return T. And so it's just showing us the nodes, right? But if we wanted a specific property off of that node, you do that with identifier dot property key. So we have remember the properties on these nodes, we have key value pairs. The key is name, and then if we ask for that, it's going to give us all those values. So this is a tabular result in the browser. It's going to give you a table that you can export as CSV or whatever you want to do. But that's the essence of graph versus tabular results in the Neo4j browser. Is that when you return the entire node, you're actually returning the entity itself. You're getting all of its properties. But you can, of course, just return individual properties as if you would a field out of a table, except we're just doing properties on nodes at this point. Yeah. The question is, what if you want the label? There's a labels function. It's actually going to give you a collection because nodes can have multiple labels. So this is actually a list or an array or whatever you want to call it. In Neo4j, it's called a collection. So that's why they have it in brackets. So that will show you all the labels on the node. But that is just on graph versus tabular results. So let's just start writing one more complicated queries. Okay, step number 1, aliasing in the return clause. Of course, you can alias your column name just like you would in SQL, where you want to say, select something as something. You can say return this property as, this column name. So here we're matching on all the category nodes and returning the name property up of those categories as category. So these are all different categories that we have in our graph. That's straightforward enough. Of course, we also have a where clause, just as you would expect from a clear language. And that can be used after a match clause. So in the match clause, you'll draw your pattern, and then you might want to filter that to only graph certain nodes within that label. So let's say you match on place in category, and then you only want category nodes with name barbecue, which is just one node. You only have one category node with name barbecue. So here we're matching on all of the places in the barbecue category, essentially. And so here, we've assigned a variable C, or an identifier C, and then we're saying that the name property on that node has to be this string. So hopefully that's not too different than the where clauses you're used to. and then we're returning the name of the place. So here, we're using the P identifier that we assigned all the place nodes to as barbecue.
Can you do any wildcard?
Yeah, we'll get into that. Questions about wildcards. Yeah.
Some form of autocomplete.
What's that?
Autocomplete.
Not built into the browser, but I have a personal project that does autocomplete. I'll definitely do a show and tell later. Yeah, so, and notice that we don't have an identifier on the in-category relationship. You don't have to assign things to an identifier variable. I typically only assign things to identifiers if I need to use them in a where clause or return clause. So you don't have to assign things to an identifier. We've only assigned the categories to C because we wanted to say where the name is barbecue. And then we assigned this to a P because we wanted to return the name of the place. Yeah.
How do you know what the things are that you can use? So for instance, that category exists, in category exists, name and label and all that.
Yeah, so the question is, how do you know these things exist? I guess you just have to know your model. There is this handy, if you go to this, that's not what I'm going to do. So if you go into the star thing in the browser, and you click on what is related and how, it'll show you all the combinations of node relationship node in your graph in case you forget. So this is nice because you might forget that you have a place label, an at-gate relationship. So this will show you all the combinations. So you might forget how something is spelled or something like that. So this is a nice reminder. But I think that goes back to the autocomplete question. There are tools out there that will autocomplete on the node labels and relationship types that you have in your graph.
This is part of what I meant, but I also meant like that name or label. Like how do I know those?
Well, yeah, that's just a matter of, I mean, there's like endpoints, there's REST endpoints to get all that information. But it's just a matter of you knowing what exists in your graph, unfortunately. So here, yeah, I mean, we can use this to say, okay, there's place labels, there's user labels, category labels. And there's queries you can write to get all the different label, property key combinations. But at this point, we just kind of have to know. But yeah, there's autocomplete stuff out there that will help you with that. Okay, this is what I like to call shorthand where conditioning. So in the previous query, we used the where clause, but you can also do the same thing within the node itself. The performance is identical. The query plan is identical, the output is identical. It's just a matter of preference. So here, we're using the curly braces within the node to say that the name property has to be this string. So within the category node itself, we've removed the identifier. We don't really need it anymore because we're only using it in the where clause. But after the label, you can specify key value pairs within the curly braces to say that the name has to be barbecue. So this is identical, it's just a matter of preference. Yeah?
Can you do logical expressions in the shorthand?
Question is, can you do logical expressions in shorthand? And that's no. You can't do like or less than or greater than. It will only do and, essentially. Because if I wanted to do another property, I'd put a comma after this and do another one. And that would just be saying and this, essentially. So I think the answer is no.
Does the same thing work for labels? Like if you have multiple labels on the node and you want to say get nodes that have both labels?
Yeah, so if you want it, that doesn't exist in this data set. If there were, the question is how do I get nodes that have, if you have nodes with multiple labels, how do I match on both? You would just keep going like that. Maybe do something like that. So you just do colon, whatever, and this would only match on nodes that had both the person and student label. If that were in your model. That's not in my model.
Is there a performance advantage
Between what?
between where and me? You wanted to just
No performance difference whatsoever. It's exactly the same. The query plan actually pulls everything down into where clause anyway. So just a matter of preference. Okay. I think answers someone's question. Fuzzy or wildcard matching. So you can do regular expressions in Neo4j. So let's say we wanted names of bar or barbecue places. So we wanted to match on both the bar category and the barbecue category. So this query is pretty similar, except we put a tilde in here after the equals. And that's saying, okay, this next thing is going to be a regular expression. So we're saying where the name property on that category node is roughly equal to this regular expression. So this will match on both bars and bar equals. But this will not use any indexes that you have. If you were to put an index on that name property on the category, the regular expressions don't use those indexes. But the next slide will show you something that does use indexes. But sometimes you need the flexibility of regular expressions. A better query would be to use starts with question.
Do you have an order by queries like here?
Oh yeah,
Categories actually ordered by category.
we'll get to that. Yeah, we have order and all that. Oh, we'll get to that. So a better query for the previous one is to use starts with. We've added in Neo4j 2.3, there's starts with, ends with, and contains. That covers most use cases for string matching. So instead of doing the CNAME regular expression, this will actually use the index on the name property if it exists. So there's starts with, ends with, and contains, and those are all used in the where clause like this.
Better performance than regex.
Yes. Well, the regular expressions don't use indexes, and this does, essentially. So always use this if you can. Regular expressions are really only needed if you need something more complicated than contains or starts with, but this covers most use cases. Yeah.
Can you use RE or the starts with keywords in curly bracket?
No.
Okay, only where clause.
Yeah, only in the where clause. Question was, can you do this in the shorthand? No. The shorthand where conditioning is only exact matching, and it's only and this and that. There's no, you can't really do anything in the shorthand other than say this property is that. Anything more complicated, you have to bring it down into the where clause. So this is the same query, but it's much better because we, number one, didn't have to write a regular expression, and number two, it uses the index if there is one on the name property on the category. Okay, aggregation. So of course, like you would expect out of query language, you can count things, you can sum things, average, min, max, all of that classic stuff is available in Cypher. So here we're matching on place in category paths, and then we're returning the name of the category and then the count of how many places are in that category. And notice the absence of a group by clause. You don't have to explicitly group by anything. It's inferred from the aggregations that you use in your return clause. So here count star, we could have done this in a number of ways, but here count star is just essentially, it's taking all of the rows and then aggregating them up by count. So all of the names of the categories and how many times they occurred. Essentially counting how many in-category relationships there are to each category. A number of ways to do this. We could have put an identifier on the place and count P instead. But that is our categories and the number of places in those categories. And to answer the previous question, we do of course have order by and limit clauses. So this is the same query, except we're getting the top 5 using an order by and limit after the return clause. So we're matching on places and categories, returning the name of the category. And we've aliased both of these things. So we named the name of the category, and then we alias the count as places. So then in the order by, we can use that alias. So we're ordering by that count of places descending. The default is ascending, but if you want to be descending, you have to supply that keyword. Yeah. User defined. Oh. No, we don't really have that user-defined functions. I mean, not as you would be used to them in SQL. We have what we call unmanaged extensions, which is totally beyond the scope of this class, but it's like you go into the Java API and write some stuff, and then you can expose it as an endpoint. But the whole, writing a function and exposing it as a Cypher function or keyword is in the roadmap, but it doesn't exist right now. Good. We have labs. So I was lying about pop quizzes apparently. We have another pop quiz. List the bars in alphabetical order. So you should be able to grab. I'm not gonna wait for you guys to do this because we have a lot of time. But list the bars in alphabetical order. We should be able to take a previous query and change it up just slightly. Here we're matching on places in categories where the name of the category is bar, and then returning the name of the place, and then ordering by the name of the place, which would obviously do it in alphabetical order. So nothing terribly new there. Okay, let's look at multiple patterns in the match clause. So in all the previous queries, we've just been doing node relationship node. But of course, you can do more than that, and that's where the power of Neo4j really comes into play, is when we start defining more complicated patterns. So here we're getting the place in category path, and then we're also grabbing the at-gate relationship from the place. So there's a few ways you can do this. You can try to fit it all in one line if you want. Usually that's pretty difficult. So you can break it up with commas. So here we have our first line is pretty similar to what we've already been seeing. Then we have a comma, and we're continuing on the next line. But it should be kept in mind that this is one big expression. It's not like the query planner is doing one and then the other. It's all at once. Whatever you define in the match clause is an entire one expression. And then you can continue on by using the same identifier in the rest of the query. So on the first line, we've bound our place nodes to P. And then we also want to get the at-gate relationship outgoing from those place nodes. So we're using that same identifier here on the second line and continuing on saying, okay, we also want the at-gate relationship outgoing from these places. Because you have places and categories, and these places are also at-gates. And then we're returning the name of the place, and then there's a number property. It's a numeric property on those gate nodes. So here we're getting the name of the place and the gate number. Yeah.
So if you didn't put the name and the number, if you just said return P and G, comma G, is that what it would give you sort of that node bubble graph thing? Okay.
Yeah, so if you return the entire entity rather than the properties, it will give you that visual result, which you could go ahead and do here for fun. Yeah, and you can also return a combination of entities and properties. You can return whatever you want. But then it gets a little cloudy on, do you want to show a picture? Do you want to show a table? At that point, you jump into the table view in Neo4j, and it'll show you kind of this JSON output of your combination of nodes and properties and what have you. But we should, for this query, we should probably also get the terminal information, so we don't have to check every single gate, 27 and all the different terminals for flybar. More likely, we want to see the terminal that the gate is at. So same thing here, except we've added another line to our match clause. We're also getting that internal relationship from the gates. So the same query as the previous slide, except now we're also grabbing from the gate nodes. So we've assigned the gate nodes to this identifier G here on this line. And then in this line, we're saying, okay, we also want the in-terminal relationships outgoing to the terminal nodes. So here we're returning the name of the place, the gate number, and then the name of the terminal. And then ordering by place. We're getting it in alphabetical order. course, your match clause can be as long and complicated as you want it to be. Okay, roughly similar query, except here we're doing, I guess, a sort of recommendation style query. And we're also using a function in there. So let's say, hypothetically, we want to see the closest copy place to gate 10 in terminal B. Well, we could keep our match clause the same, that doesn't really need to change. We want to be in the copy category, so we're saying where the name of the category is copied. And we also want to be in terminal B, so we're going to limit it to the terminal where the name is B. And then we're going to return the name of the place. We're going to return the absolute value of the distance from the gate to gate 10. We don't care if we have to turn left or if we have to turn right. We just want it to be closest to us. So we're going to use the absolute value there. And we're going to alias that as distance and then order by distance. So here we say that there's a Starbucks coffee that's 2 gates away at gate 8 in terminal B. And then these are ordered by distance from gate 10. So I guess that was just to show that you can use a function, within the return clause if necessary. Okay, let's find all of the Dunkin' Donuts locations. Again, we are short on time, so we're just going to jump into the answer. Same query, except here apparently I've decided to use the shorthand conditioning, saying that the name of the place is Dunkin' Donuts. I assigned it to identifier called donuts, and then we're getting the gate and the terminal. So we're returning the name of the terminal as terminal, the number of the gate, and these are all of our Dunkin' Donuts locations in Dallas-Fort Worth. So if you're flying home through the FW later, you know where to go. So nothing terribly new there. Okay, let's get into some fun stuff. Negating patterns in the where clause. So in some cases, you might want to assert that a pattern does not exist within your search. So you can actually specify patterns in the where clause. So here, we're looking for many pairs of users who have both liked Blimpie but are not friends with each other. So here in the match clause, we have I shouldn't say 2 users, because it can be more than 1 pair. That should just say any pairs of users have incoming liked relationships to the same place, where the name of that place is Blimpie, and not you want friends with you too. So here we're saying that this pattern cannot exist. So we're using the same identifiers that we bound them to in the match clause, U1 and U2, and then we're using this, we're specifying that this relationship cannot exist between them. And notice the absence of direction on the friends with relationship. You can omit the direction in your Cypher query if you don't care which way it is, because intuitively, a friends with relationship, it's bidirectional, right? I mean, if I'm friends with you, you have to be friends with me, typically. But in Neo4j, you have to store things with a direction. They necessarily need a direction, but they can be arbitrary. They can pick a direction arbitrarily when you write the data, but then when you read the data with the Cypher query, you can just omit the direction. And it's the same performance as if you would specify direction when there's only one relationship there. It's an anti-pattern to specify 2 friends with relationships. You don't want one going one way, one going the other. That's not necessary. Unless it's something like Twitter, where it's like, if I follow you, you don't necessarily have to follow me back. So if we were to be modeling something like Twitter in Neo4j, you would want those 2 relationships one for each of the follows. But in a Facebook style graph, where me being friends with you means you have to be friends with me, you don't need to store both directions, you just store one of the directions arbitrarily. And then when you query it, just omit the direction in your query. It's a common modeling question about Neo4j, so I like to cover it. So this should find us a pair or any number of pairs of users who have both liked Limpy but are not friends. So clearly, Ian and Bob like Limpy, but they're not friends. Maybe they should be, because they both like Limpy. So the lab here is to find places that Alice has liked but not checked into. We would just do the same thing here. We're matching on a user liking a place where the name of that user is Alice and not Alice checked into that place. So this user has a like relationship to this place, but cannot have a checked into relationship to that same place, is what this query is saying. And so there are a handful of places that Alice has a liked relationship to, but does not have a checked into relationship to. Hope I'm not going too fast. I want to get as much as I can in here. We have like 20 minutes left or something. All right, let's do the, so this query doesn't have the optional match clause in it, but we're building up to it. So this is users and how many friends they have. If using match on its own, users who have no friends won't be matched at all, because the match clause is what I like to say, or what I like to call all or nothing. So if exactly what you specify in the match clause, if any part of the match clause, if any part of the pattern doesn't exist, then it's not matched at all. Because it's not like it's incrementally saying, okay, let's match on the users, and then let's find the friends with relationship. It's the entire expression is being matched on. If any part doesn't match, that result's not going to be included. So any users who don't have this friends with relationship, they're not included in this result set at all. So here we're only seeing users who have one or more friends. Because we're matching on the user and then counting people on the other side of the pattern of the relationship as friends and ordering by that descending. So here we only have users who have one or more friends. But the optional match clause will, as it suggests, will optionally match on the pattern that you specify. So first match on the users, then optionally match them having a friends with relationship with other users, and then the return in order is the same. So now we're also getting users who have 0 friends because we specified that part of the pattern in the optional match clause. And you can think of an optional match as kind of like a full outer join, if you will, between.
If in that case you were matching on the friends with instead of the F:"user, would you still get exactly the same answer? Like, can you do a count of basically the edges as opposed to count of the nodes?
Yeah. So I think actually this I might answer your question later. Well, yeah. You see, so you don't want to. Well, yeah. So the people who have 0 friends have a count of 1 right now because we're counting. So count star is usually not a very good idea because you don't really know what you're. You have to kind of really know.
What I meant is if you just called colon friends with, if you called that F, can you do count F and then give you exactly the same?
Oh, I see what you're saying. Yes. I thought you meant to count. So I'll answer the whole like counting degree thing I think later. But yeah, so this will count the number of those edges, which is in most cases identical to counting the number of nodes on the other end. there can be some gotchas around there. Sometimes you need to put a distinct in there if you have duplicate nodes, but usually that's not an issue. So yeah, you can do the same thing by counting the number of edges. Okay, so the size function is a brand new keyword in Neo4j 2.3. In many cases, it replaces optional match, depending on how you're using optional match. In this case, we could replace optional match with the size function, which is much, much faster because it uses, it actually uses something that's cached on the nodes. Internally, we have stuff cached, stuff like the degree of a node by its relationship types. So this is just a constant time operation right here, where we're matching on the users, returning the name of the user, and then the size of this pattern as friends. And so this will be much faster and is giving the same data. But however, if we wanted to do something that involves the data on the other side, like if we wanted to get the names of those friends, we'd have to go back to optional match, right? The size is just going to do a count for us. It's not going to retain any of the data of the nodes that were on the other side of the pattern. And size, within size, you can specify multiple length patterns. It doesn't have to just be node relationship node. There's lots of ways to use size. But in this case, size can replace optional match. It's just counting how many times this relationship, the degree of this relationship type to this node u over here that we matched on. But however, going back to, let's go back here. If you wanted to, kind of jumping ahead here because I haven't talked about one of these things yet. But like if you wanted to say, if you wanted the names of those friends, you would have to use optional match, right? Because you need to assign this to something and then pass it to we'll talk about the collect function later. But the point is that if you care about the data on the other side, you're not just counting, you gotta use optional match. If you're just counting, usually size is the way to go. I think we'll talk about the collect function very soon. Yes, excellent. So the collect function, it's kind of like group concat in SQL. You guys use group concat? Okay, one person is using it. Excellent. So it's just like a counter set that's going to actually collect, whatever you pass to it up into an aggregate function. It's going to collect it up into a single row. So here we're matching on users. We're optionally matching on users being friends with other users, returning the name of the user, the count of friends, and then the collection of their friends' names. So this will show us how many friends they have and the names of those friends as a collection, and then ordering by that count person. So that's how the collect function is used. It should be noted that the friends' names column, I should probably change this to add brackets around it. In the browser, it should put brackets around that because it's not a string with commas in it. It's a collection of strings. Let me go in here. So what it should look like. And then, of course, these people have an empty collection. They don't have any friends. And then you can refer to specific indexes within that collection with just like this with brackets and then an index of some sort. But as is, it's going to be collections with individual elements. All right, the with clause. So for the most part, anytime you want to do a filter or you want to use like some sort of aggregate within the where clause, you need to carry it over, as I like to say, in the with clause. So let's say you want to find users and how many friends they have, along with the names of those friends, and only show me users with 2 or more friends. So you can't say where count f is greater than 2. You can't use an aggregate on the fly like that. It in a where clause, you have to first determine it in the with clause, and then you can use it in the where clause. So this is typically what a query will look like. It will be match with where return. And you can do this as many times as you want within a query. You can do match with over and over until you get to exactly what you want. The with will it'll carry over everything that you want to continue on with your query. And as soon as you don't include something in the with clause, it's out of the namespace. So if you don't carry it over in the with clause and then you try to return it, it's going to throw an error saying, sorry, this identifier is not recognized or something. So if I up here in the match clause, so like, for example, I've bound the users to you. But here in the with clause, I've only carried over the name. I haven't carried over the you itself. So if I try to do something with that identifier down here in the return clause, it's going to give me an error saying that doesn't exist in the namespace anymore.
Can you refer to one field within another? For example, can you collect F name as friend's name and then count friend's name as friends?
So you're saying,
so put the count after the collect and then just do count friends' names as friends.
Let's learn together. You're saying you want to do like I don't think like this. As I can't imagine it. So many things have changed in I keep getting bitten saying things aren't possible of new Neo4j 2.3 and then they change something and it is. And then it looks silly. That you can't refer to something within the same, scope as you are defining it. That makes sense, though. You'd have to do that in another with clause. If you wanted to do it that way, you'd then say with user friends names count as I think I spelled something wrong. Anyway, usually, this is the typical way. This is how I do it: is do a count and a collect within the same with clause. Right. So this is just more things that you would do with a with clause. So if you wanted to say that they have to have more than 2 or more friends, and Hank has to be one of their friends, that's another thing that you want to specify. You have to first determine the name of their friends with the collect function, and then say that the string Hank is in that collection. And that's how you do things with collection. You say that this value is in this collection. So same query here, except we put another filter on it saying Hank has to be in that collection of names. So now our result set only has people with 2 or more friends, and Hank is in that collection of names. Okay, or with relationship types. So you can specify, I think that's the best way to say it, is or with relationship types. If you want to say, like, fast food places that Alice is either liked or checked into, you can use this pipe to say, I want to match on this relationship type or that relationship type between these 2 nodes. So here, we're matching on a user, and then we're traversing the liked or checked into relationships. And we can use the same syntax here where we assign that to an identifier with identifier : relationship type. But then beyond that, it's just pipes. You don't specify another colon after the pipe. There's only 1 colon. And then beyond that, it's just pipe delimited relationship types to say this or that. And you can do that as many times as you want. And then we're getting the place and the category of the place case, so yeah, fast food places. The category is fast food, and the name of the user is Alice. Entering the name, and then we're collecting all the types of those relationships. So the type function is a Cypher function that when you pass an identifier from a relationship, it'll show you the type of that relationship as a string. Here we're seeing that she liked Burger King, she checked into McDonald's, and she both liked and checked into Pizza Hut Express. So the type R is just it's referring to the identifier R that we assign that relationship to. And then we're collecting it in the case that it's both. Yeah.
You have distinct.
Yeah, there is distinct. So you could do, yeah, it's a qualifier on like, you could do count distinct. It goes inside the count. It can go inside collect as well. I don't think we have any examples of that in this slide deck. But you do something like, it's not the case here, but you could do something like this. You would throw the distinct right before it. And you could do that in count and collect. There's multiple cases. You can do it in front of a return. So distinct, if you have any duplicates, it'll bring it up in the distinct rows. So it can be in front of your return values, or it can be a qualifier, I suppose, within your count and collect all of your active functions. Yeah.
Maybe, I'm not sure if you'll have time, but is it easy to find the second degree friends of someone?
Is it easy to say that again?
Second degree friends of.
Yeah. Maybe we should jump forward into the coolest part of Neo4j. None of this is important, don't worry. So let's do this. Everyone on the slides jump to the paths part of this is what Neo4j is really good at. Is these variable length paths. So let's fly through this really quick. So who do Charles and David know each other through? They could be direct friends with each other, or they could be friends indirectly through a series of hops between, however many people. We don't know. And we want to ask the graph to find it for us. And you do that with the asterisk here. So all of our previous queries were doing length 1 queries. They were doing one hop only. If you want to do multiple hops, this is doing any number of hops. You put the asterisk in there. So this should find all the paths between Charles and David. You see that there's a couple here. One of them is longer. It goes through Alice, Forrest, Elaine, Hank, David, and then one of them is shorter. It goes through Alice and Hank. So that's how you do variable length paths. Yeah.
When the result first comes up as a graph, is there any relationship where how this is equals to the zeros will be like that, or is it just like fitting into the
I can't hear you very well.
when the result first comes as a graph, it has certain structure, like some nodes are closer, some nodes are further away.
Yeah.
Is there a specific relationship in that, or is it just
No, I can't imagine there's anything particular going on there. It's just, this is some fork of D3 that's displaying your graph for you. It's not a function of any of the data in terms of how it's displayed. Okay. And this is just to show you can wrap paths in a length to get the length of the path. So the browser result can sometimes be somewhat confusing. I mean, especially when you have a visual result, it's hard to look at this and say, oh, there's two paths here. So it's nice to wrap that in something that will show you on a row by row basis what's going on. So there are two paths returned, one of length 5, one of length 3.
On that example, there's actually no connection where David is friends with somebody who is eventually friends with Charles. So how do you get the direction captured?
Well, I omitted the direction. That goes back to what I said earlier. With this friends with relationship, it's more or less arbitrary. It's like if I'm friends with you, you have to be friends with me.
I guess what I mean is if you put, say, the greater than sign again
Yeah.
next to the B, does that mean everybody in between has to collectively be friends?
That's a
Like,
good question. So if I were to put the arrow in here, yeah, all the relationships along the path have to be in that direction. And so in this case, I don't think anything would be matched because there are none for all of them. But that's, it's arbitrary, so I leave it off because I don't care which direction it is. All right, let's get that. And then you can also specify exact path lengths. So here I'm saying it has to be exactly length 3. And then this stuff is just it's going through all the nodes in the path and extracting that name property off of them so that we can see all the names of the people in a tabular result. So here, nodes is a Cypher function that gets all the nodes out of the path. So here we're passing that path to the nodes function. And then we're essentially saying for each node in that path, show me the name property as this collection. So that's the names of people on that path, and then the length of that path as a path. So this is to show that we're only matching on paths of length exactly 3. And then hopefully I have it in here. Yeah, you can also do ranges within this asterisk qualifier. So here we're saying that we want paths up to length 5. So you do that with dot dot, where the default minimum is 1. So here we're doing 1 dot dot 5 essentially. And then the minimum could be whatever you want. You could do 3 dot dot 5. So same query here, except we're just doing different things with the range here. So this is the most powerful thing about Neo4j is these variable length paths. Yeah.
Instead of path length, can I use a variable defined relationship? Weighted. So it's each link is 1, right?
Yeah.
Let's say if there's a weight on it.
So you'd want to return like maybe a sum of all the properties on a relationship?
Yeah.
Yeah, you could easily do that with there's a reduce function. So that's I can probably figure out an example, but you can go to the Cypher ref card. Type in Cypher ref card into Google, and it should be the first result. It'll show you all the different stuff you can do with Cypher. Reduce would allow you to iterate over that collection of relationships and sum all the properties on them. I don't really have time to, because I know our likes relationship has some properties on it. Maybe if we can get through the next few slides, I'll do that for you. Let's skip the shortest path. So Cypher has shortest path built into it. It will only do shortest path by the number of hops. Weighted shortest path is on the roadmap. But here, if we hypothetically wanted to get the shortest path between Greta and Wendy's, we would wrap the syntax within shortest path is the same, where you draw the graph pattern you're interested in with nodes and relationships. But you wrap it in the shortest path function, and then you can assign the entire thing to an identifier just like we have been. So here we're finding the shortest path between two nodes, a user node and a place node, where in the where clause we're specifying which nodes we want to start and end at. And then in the middle we're saying it can be any relationship type, and we don't care about the maximum length. In shortest path you can get away with not specifying a maximum length, but in a regular batch you usually almost always want to do that, because otherwise your graph will just search endlessly for every single length path, and you'll run out of memory in that kind of time. So usually you want to specify a max if you're doing something like this. You want to specify a maximum. Doing just the asterisk by itself is almost never a good idea. It will just exhaustively search for all length paths, which is not usually a question you want to answer anyway. So So specifying maximum, but in shortest path, you don't really need to do that because once it finds the shortest path, it's done and it can answer it. So this will show us the shortest path between Greta and Wendy. So you see Greta liked Pizza Hut Express. Pizza Hut Express is in the fast food category, and so is Wendy's. So we didn't put any specification on, what kind of relationships it's allowed to traverse the shortest path. But more realistically, we want to specify some type of relationship. Say, we can only specify, or we can only traverse these types of relationships.
Does it always only return one? Like if there are ties?
Yeah.
It just arbitrarily chooses one path?
Yeah, that's right. So the question is, does it arbitrarily just choose one in case it ties? And the answer is yes. It will just choose one of them and return it to you. But I think the next few slides, we'll be talking about all shortest paths. This will return all shortest paths in case it ties. So in this query, it's exactly the same, except we specified that the relationship type has to be liked. So that's the only relationship type that we're allowing the shortest path algorithm to traverse. And now we see that we got a different shortest path only through liked relationships. So Greta liked her natural snacks. Charles also liked her natural snacks. And then Charles liked Wendy's. So a very quick and easy way to find how two entities are related.
For the last query, I actually got two patterns.
You can only get one with shortest path. It's possible if you were on the all shortest paths. Are you using all shortest paths?
No?
No. Well, we can look at it later. All shortest paths should only give you one path. But in the case of ties, so shortest path is just giving you one of those paths. If there are multiple paths that tie for shortest path. But all shortest paths will give you all of those paths. So same query here, except we've wrapped it in all shortest paths instead of shortest path. And we see that we got two paths here. So there was a tie, and all shortest paths will show the we're mostly out of time, but Neo4j has constraints and indexes. You can create uniqueness constraints on label property pairs. So you can say users have to be unique by name. So that's the syntax for that. Assert that the name property on the user is unique. And that would also create an index on that label property pair. So if you're doing a lot of lookups on node labels by certain properties, you want to have an index on that. And then in most cases, you also want a uniqueness constraint, so you don't have data that's duplicated in your graph. If you add data that violates a uniqueness constraint, it will reject it, so you have to clean up beforehand. Typically, you want to create a uniqueness constraint before you've even added data. If you create a uniqueness constraint and then you violate it, the entire transaction will be rejected and rolled back. You can create indexes. So in the cases that a uniqueness constraint is not appropriate, you can also just create an index on a label property pair. And I'll end on that note. I think we're all out of time. Any last minute questions? Yeah. You.
I discovered if you double click on the node, it pops up a bunch of other.
Oh, yeah.
Can you explain that a little bit?
Yeah, so when you double click on a node, I forgot about that. If you double click on a node, it's actually just writing a query, match node ID, give me all the relationships, and then display it. So that's all that's doing. It's finding all of its neighbors and displaying them to you.
Can you put it back?
You can't pull it back, so double click carefully. No undo. Any other? Yeah. You.
Are there any ways to support Facebook's GraphQL language as a front end?
Yeah, I've actually started working on that. We've talked about it a lot internally, about writing some interface for that. So yeah, probably. I don't know if it'll be an official Neo4j thing, but I've definitely looked at it.
It seemed to me like all these nodes only have like one label possible. What if you had several?
Well, yeah, nodes can have several labels.
Okay.
And then the colors, you can choose which color.
Well, what I meant though is like name and say gender and age and all that for like a person. Is that
I don't understand.
a node could be a person. A person has several attributes.
Yeah.
You can specify all the attributes.
specify. Oh, you can't show all of them in the browser. You have to pick one.
But I mean, it can have several.
It can have multiple.
Okay.
Nodes can have as many properties as you want.
Okay.
Thanks, everybody. Let's go.